Yeah, another very active person, Dr. Krishna Kumar and Dr. Vijay. They are also very dynamic persons and they are contributing a lot in this department and also the coordinators of this program. So I also welcome learned faculty of this department who are mostly we have young faculty members, so I also welcome them. I feel proud to mention that we have more than 200 participants from different organizations, academia, and industry. They are faculty members as well as students also. So I welcome them with loving hearts of all present here. And the last, I welcome one and all who are participating in this FDP program,
It's my pleasure.
offline and online both in the both mode. Thank you very much.
Thank you, sir. This FDP is on novel material, and the main content which we are going to cover in this FDP are novel material. And this first is nanomaterial is the oxides, nitrides, alloys, and composite synthesis and application of energy. This lecture given by will be given by the Dr. M.B. Reddy. It is from the Canada, and it is one center. There is Center of Excellence in the Transportation, Electrification, and Energy Storage. Earlier, he was in NOS, National Institute of Singapore, studies there. And one we want to cover that is the CNT based sensors. This lecture will be given by the Professor Suresh Prakash Arsa. He is from the IIT Roorkee. Another today's lecture is one more lecture is given by the Dr. Rajendra S. Dhaka. He is the associate professor in the IIT Delhi, and he is giving the lecture on the sodium ion batteries. This is used for the energy storage. And one lecture, he is very young person, and he is the uh, covering one sentence by medical engineering and assistive technology. It is very innovative center at the NIT Durgapur, and Dr. Tushar Kanti Baya, he is giving lecture on some health monitoring nanomaterials. So it is very innovative system, novel material is covered by the Dr. Bera. And one more lecture given by the biomaterials, because this novel material this cover all the materials which are used functional materials. So this is our very eminent person, and it is the alumni from MNIT Jaipur, Dr. Ashok Ram Raichur. He is the professor at IISc Bangalore in the Department of Materials Engineering. So, and one more, this is some about the thermal properties of the this material. This is covered by the Professor Ambir Singh. He is from the University of Rajasthan. And lead-free ferroelectric. This another kind of the electric material. This lecture given by the Professor Sanjeev Kumar. He is from Punjab Engineering College, Chandigarh. And since magnetic set memory alloys, it is also important. So this is and some of the thermoelectric material. These are very important for the as a novel material. So this lecture given by Malay Kumar Banerjee, M.K. Banerjee. And this some of the one of more important lecture that is on the biomaterial. It is the given by Professor Arvind Sinha. He is the chief scientist and head in the Advanced Materials and Process Division, NML, Jamshedpur. So we gather all these topics by different speakers, and we collect the speakers from the throughout the country. As our participants from throughout the country, since from the MNIT, there are very few number of the participants This is okay. Sorry for interruption because some network is held. ये जो रिकॉर्डिंग हो रहा है रिकॉर्डिंग करना okay, so this is and so this sorry for interruption due to the network of this so network here, and all the participants they are throughout the country. So it is our fortunate that all you are joining from throughout the country, and there are some limited seats, 200 seats. So 250 applications we received from the all the applicant, and we accept only 200. So rest 50% they are not going to join this course. So we are apology for them. And so now I request our head of department to enlighten some our achievement of our departments.
Thanks, Dr. Duchania. Am I audible?
Yes, yes.
So good morning to one and all. Chief guest Professor Gunwan Sharma, Dean RNC. Guest of honor Professor Upendra Pandel and Dr. R.K. Duchania, Dr. Vijay, Dr. Krishna, coordinator of the faculty development program, and eminent speakers, professors, scientists, and my dear faculty members. It is my pleasure to welcome you all on behalf of the Department of Metallurgical and Materials Engineering, Malve National Institute of Technology, on the occasion of Faculty Development Program on Novel Materials, sponsored by AICT under the scheme of ATAL. I am happy to share with you that this new year was started with the novel vaccine donated to the or gifted to the nation. Similarly, our department has started this new year with novel materials. The Department of Metallurgical and Materials Engineering is one of the oldest department with its reputation for the more than 55 years. The department offers UG and PG programs. Both the programs are accredited by NBA. And the department also giving education to more than 10 full-time PhD students. So far, department has produced several eminent speakers who are in the top positions. Few of them are Dr. A.K. Suri, Dr. or Professor A.M. Raichuri, Professor Nikhil Gupta, and many more who are in academic institutes, who are in top national, international research organizations, and many of them are environmental engineers. I think this is unbelievable, but this is true. And many metallurgists who have passed out from our department are in Intel also. So the department works in the area of traditional metallurgy to the advanced area like nanomaterials, composites, nanomaterials or nanocomposites for the electronics application, for the typological application, for the energy materials, and graphene also in different forms for different application. Shape memory alloys, light metals and alloys, high entropy alloys for corrosion protection, etc. We have more than 15 research laboratories where our researchers are working in different areas. We also have high-tech instruments. Some of them are dilatometer, which works up to 1500 degrees Celsius. We have high-temperature differential scanning calorimeter. We have multi-viewer optical microscope. This is the instrument which are in only few institutes. And we also have a high-tech universal tensile testing machine. The department has received research funding of more than 439 lakhs rupees in last 5 years. And we have completed research projects funded by BRNS, DST, DRDO, Ministry of Steels, and research projects of more than 500 lakhs rupees are under review. I hope that shortly we will get good news and we will give this news to our faculty members, students, and alumni. Annually, the department publishes more than 15 research papers in reputed international and national journals. And the department also publishes good quality papers in proceedings. And every year, more than 10 to 15 students qualify GATE exams, and 4 to 5 students get the admission in top management institutes. And many students are also get the admission for master's degree in foreign universities, IITs, and other top universities. And I am also happy to share with you that in the COVID period, means in the last 6 to 8 months, the department has organized more than 6 faculty development programs, short training programs, who have benefited more than 1,500 faculty members and research scholars. And this is really a good achievement for the department. And we have also organized many one-day, half-day workshops to provide the education or training to our students and faculty members. I believe that this faculty development program will immensely benefit all the faculty and research scholars. I wish for a grand success of this faculty development program. Thank you.
Good morning, all of you. First of all, I would like to be extremely grateful to all the organizers who are present here, Dr. Upinder Pandey, Dr. Vitania, Dr. Vijay, and who have been directly or indirectly contributing to the bit of the students as well as the researchers in this institute as well as outside. I am also happy to be here and RPQL, who is also present and who is going to contribute a lot in this present FDP, which is being organized under the ATAL scheme of AICT. Initially, 9 trust areas were identified by the AICT under ATAL project, and they were artificial intelligence, Internet of Things, IoT, then blockchain, robotics, quantum computing, data sciences, cyber security, 3D printing and design, augmented reality, and virtual reality. So these were the 9 areas which were identified under this ATAL scheme. But later on, the new emerging areas were added by the ATAL Academy of the AICT, and will now be conducting series of training programs like in engineering, management, arts and crafts, design and media, life skill management. So this program is under the engineering programs, and you will be glad to see that you will be having a rich, experienced faculty who is going to train you in the area of nanomaterials and novel, whatever is the theme, novel, we call it in brief, abbreviated form, ACC. So AICT ATAL scheme, under this particular scheme, ATAL, number of series of training programs have been conducted in the emerging areas across the country. In 1920, total 185 training programs were conducted in the year 2019-20. The vision is to empower the faculty to achieve the goals of higher education such as access, equity, and quality. And the objectives are to support the technical institutions in fostering research, innovation, and entrepreneurship through training. So AICT is going to achieve a world record of training almost 1 lakh people under the FDPs which are conducted under the ATAL scheme. And I'm happy to tell you or inform you that 1,000 online FDPs in over 100 emerging areas will benefit almost 1 lakh faculty members across the premier institutions like IITs, NITs, and triple ITs. This year, the online FDP programs will cost almost, you can say, 10 crores of rupees. Out of 1,000 FDPs, 499 FDPs have already been completed with more than 70,000 faculty members already trained in various areas. Digital learning and the increasing use of smart devices such as computers, smartphones, and tablets have enhanced the student learning, as well as the learning of the faculty members and the various users as well. The CBSE teachers have been trained under the flipped classroom and the blended learning concepts. I am very happy to tell you that FDPs which are conducted under ATAL scheme by AICT are the need of the hour. With this, the teachers of higher educational institutions will educate the students according to the industry needs and equip them with variety of skills. In challenging times of coronavirus, these programs are being run online. Resource persons across the globe are able to take the sessions during the online nature of FDPs. And I'm very happy to note that at least 15 persons are there from the various institutes from Canada as well, and from ISCs or IIT Roorkee and Kalazingam University and many other universities, and they will be directly be in touch with you over the course duration. So I hope that all of you will be taking the advantage of the speakers. You will be benefited with their knowledge and which are being utilized by you people in your normal lecture deliveries as well. Thank you. Thank you.
Thank you, sir. So now I invite our Dr. Krishna Kumar to give a vote of thanks.
Good morning, all of you. Am I audible, sir?
Audible?
Okay. So, good morning, all of you. On behalf of myself, committee member of this ATAL Faculty Development Program, and entire fraternity of this institute, MNIT Jaipur. First of all, my sincere thanks to Almighty God for making today's event a grand success. By His blessing and grace, we are able to make this event a successful one. It is my privilege to propose a vote of thanks and acknowledge the contribution of those who worked hard to make this event possible. I personally thanks to our Honorable Director, Professor Uday Kumar R. Eragatti sir. Due to his blessing and kind support, we are able to make this event possible. And I would like to thank Professor Anil D. Swasrabuddhe, MP Punya, Vice Chairman of this AICTE, Dr. Arvind Kumar Soni, Director, and Dr. Girdhari Lal Garg, Assistant Director of this new program of learning initiative taken by AICTE ATAL, and his vision towards making India a place which is known for its wisdom since many years. My sincere thanks to chief guest of today's event, Professor Gunwant Sharma, Civil Engineering Department. Also, he holds the post of Dean RNC, MNIT Jaipur, for his kind presence and support. I give a really heartful vote of thanks to all the speakers of this FDP who has spent his busiest time gracing this event. Your thoughts and knowledge about the subject area will enlighten our mind and would show a new direction to look into the research area. Now, I like to thank our head of department, Professor Rajan Kumar Goel sir, for his kind words and support to make this event a successful one. I, on behalf of this FDP team member, thanks to all the participants across the world. Without your support and sincere attention, this event would not have been possible. I hope your kind presence and good interaction in each session of this 5 days FDP will make this program a grand success. This type of events cannot happen overnight. The wheels start moving around a week ago. It requires planning and bird's eye for details. It has been supported by a team of very hardworking and dedicated personalities. So therefore, last but not the least, I thank to the backbone of this event, Professor Upen Pandil sir, Guruji, Dr. R.K. Duchania, coordinator, Dr. Vijay Kumar, Vijay Navratna Nadakudru, coordinator, and Professor R.K. Goel sir for their sincere effort to make this FDP successful. And in the last, I like to thank all the participants and all the PhD student, PhD, MTech, and UG student to make this event a successful one. So thank you all, sir. Now I take request to start this lecture session by one of the eminent speaker. So now it's to you, sir.
Thank you, Dr. Krishna. So after this, we are going to start our lecture. So I request Dr. Reddy is there.
Yeah. Yes, I'm audible, sir. Yes.
Yes.
Okay.
Yes, yes. Dr. Reddy, yes, yes.
Okay,
Please,
I'll start.
yes, sir. Okay, good morning, sir. And very heartily welcome of you in this FDP. And sir, you have a vast experience as I see your CV on net. And it is our privilege, and me and our department, our participants, everyone, we have the privilege that you are in our, you are going to lecture in this, talk in this FDP. Sir, please.
Okay. Thank you very much, sir. So maybe first I'll show my slide, then sir, my slide is visible, sir.
No, sir, no.
Visible.
Yeah,
Yes.
it's visible, sir.
Yes, visible. Yes, now
Yes, visible.
Okay.
Yes.
Okay. Again, okay. Now I'm going to start. So good morning, everybody. So my name is M.V. Reddy. So I call as made it as very simple, like Reddy. First of all, I would like to thank Professor R.K. Goel, head of the department, and also conference our workshop organizer, Professor Guchel, R.K. Guchel. It is like surname is a little bit different, and also the dean, and also other faculty members at NIT Jaipur, MNIT Jaipur. In fact, it's my privilege. First time I'm giving the talk, and especially one of the oldest, metallurgical institute in the India. In fact, you people have a strong, good reputation. So today I'm going to talk about on the novel, in fact, nanomaterials in terms of the oxides, nitrides, alloys, and composites. Especially since there are some already mentioned in the chairman. I think all people are coming from different parts of the India, so that I want to make it a little bit simpler so that you will be able to follow my slides. So in fact, we know that metallurgy or material science engineering is a broad topic. In fact, in this workshop, different speakers are going to cover a different area. In fact, I'm slightly focusing on mainly on lithium containing comp like energy storage or energy materials. I think next maybe third talk is going to be given by especially sodium type of energy storage by another speaker. So since I'm going to give a first talk some slides, maybe some introductory slides I'm going to give, so that will be useful for those who are students starting to, especially the younger researchers. So this outline of my talk. So if time permits, I'm going to add some fluorides and oxyfluoride if possible, since so these are the new materials people have been focused. Before I would like to introduce, so I'm coming from Canada, so presently I'm in Quebec. So this is a French and English speaking colony. So that's why we have to speak French. And also, so presently we are in the Hydro-Quebec. So Hydro-Quebec mainly working in the area of hydroelectricity, in addition to energy storage and electrifications, especially our centers and energy storage materials. Especially here you can see nearly 4 type of seasons we can see, especially during January and March, some few days in 10 to 15, like nearly 1 or 2 weeks or 10 days depending on the yearly. We can see almost like some days it will go to minus 25 to 30, and sometimes heavy snow we can see with a few days, and other beautiful season we can see. Regarding that, our institute, we closely collaborate with McGill University. In fact, they're also one of the oldest material science, metallurgy and material science engineering department. Otherwise, in other part of the university. In fact, this year, I think last year is the 50th year of the innovation of the Hydro-Quebec. Since regarding my experience, I trained in the area of material science and engineering. In fact, last 15 years, I was there in National University of Singapore. So both physics and material science and engineering department. In addition to my research, in fact, I was actively involved in the training the students, especially starting from the high school and junior college students. Also, I was involved in the especially Material Research Society Singapore. In fact, some of the conference organization and physics. Okay, and also some of the editorial board committee, and mainly some of the things I'm going to. So these are the small group. In fact, 3 to 4, nearly 3 PhD students from the Singapore. Rest of the nearly 4 to 5 students have been trained from the outside, especially from India. And also you can see that bottom slides, you can see a lot of young students. We can see here, we can tell that when we are in Singapore, it is a nice opportunity to train a lot of the junior college students. In fact, many students that we were able to, it's almost like the 10-year output. In fact, every year, many students, they can visit like 4 to 5 batches. They can come at the different times. They can do the project in the area of material science engineering. They can do, it's almost like 7-8 months program. I think people can access the lab easily and they do research. And at the end, these students are able to participate in the national and international conference. And at the end, we are able to publish some few papers based on the Scopus-based journals. So also I would like to we've been extensively some of the, especially here during when I was in Singapore, it was near to India. In fact, we have helped many people, especially PhD students from part of university, as well as people from the IITs and NIITs, etc. So now I'm going to start my talk. So I'm going to introduce my topic. So we know that from early history, human prosperity material has been interrelated, starting from Stone Age, Copper Age, Bronze Age, and Iron Age. In fact, the metallurgy, we know that iron at the time, people have learned how to make iron by using the charcoal or with the carbon, you can reduce the metal. I think this is the way we have done evolution. In fact, Silicon Age made them to think about, especially ICs, and also, for example, like batteries, one of the mobile phone you every day we're carrying. So here in the mobile phone, it contains a lot of, especially it is made from very interesting discovery from the materials or metallurgist. If you see, for example, you see the casing, we need a what they call lightweight materials, and you see the IC chips, everything made from the materials discovery. Also, one of the important device people are using the batteries. In fact, that made them to revolutionize the things. So I'm going to discuss about some of the energy related battery materials. In fact, recently what we call as energy and environment healthcare, I think these are the very important areas we are concentrating. So classification of the material, you see that depending on the utilities or depending on the utilities, materials are broadly classified. For example, building material, electronic material, and energetic material, or for example, engineering, if you say steel, iron, steel, and superalloys, and pharmaceutical and biomaterial. Depending on physical properties, we broadly classified metals, semiconductors, insulators, and magnetic materials, optical material, dielectric, and radioactive, and last one is energy material. So it is for the use of the energy storage. And again, Professor already suggested that functional material will play an important role in the area of the especially energy, water, and healthcare. In fact, energy also we can get in the different sources starting from solar, hydro, and battery, and wind, etc. In conclusion, I can tell that energy materials are and the technology is interdisciplinary area of material science and materials engineering. In conclusion, I can tell that materials or metallurgy or material science engineering deals with the material structure, processing, properties, and the applications. So what are the applications of energy materials? We know that presently we are facing the problem of the environmental pollution. For example, due to gasoline vehicles, or its batteries, one of the devices people are thinking to store, for example, solar energy or wind energy to run the electric vehicles. I think energy materials will play an important role to solve the future, especially to reduce the environmental problems. So these are the major things. That's why nowadays all over the world people are spending the. One more example. Sorry. So one more example is you see the current climate problems. In fact, I think people are not only India throughout the all over the places heavy especially vehicles. I think including here also they're spending a huge amount of investment in the area of how to reduce the pollution, especially in the highly dense population cities. So again, I'm going to introduce, for example, any property of a material depends on the, for example, composition, microstructure. In addition to the, especially microstructure depends upon the especially how we are going to process. Also, it depends on composition. In fact, in literature, people have been adopted in the different type of performance of novel made either by novel methods of processing or nano-sized approach or nanotechnology or search for the new material. In fact, remember, searching for new material is not so easy, although the formulas are many things have been discovered. So sometimes looking for new materials is going to be a lot of time and effort. At the end, after succeeding only few materials, we can use it for the real applications. So in my talk, I'm going to tell, so since I'm going to talk about sometimes nano and submicron size, sometimes remember nano, I think all the people might have known with working with the materials. Nano we call as starting from 1 to 100 nanometers. And also remember, sometimes we don't work too, especially for batteries, we don't see too highly. In fact, minimum is 10 to 15 meters per gram is like that is the lowest one. And some cases we are able to do with high surface area material also. Sometimes submicron size is above 100 nanometer. Again, we can see that nanomaterials have a compared to the bulk material, nanomaterials have a different type of the interesting properties. That's why people are using for the miniaturized applications. In one example is what are the in comparison to the nano size to micron size. Due to the high surface area, will give the shorter diffusion length and will give better volume variation. We can see as a consequence, we can see the improved energy storage. These are the various nanomaterials. I think people can look into the whole slide where in the various in terms of water, healthcare, and then different type of the applications. In fact, anyway, there is a very old data. Still, there is a huge growth in this type of the materials. So now I'm going to talk about the regarding my topic, material processing and characterization techniques. So these are the various nanomaterials. We can starting from the particles, plates, rods, and strips, and nanoporous, and fiber, nanowalls, etc. People can get. In fact, these materials you can prepare by using different approaches or by chemical or physical methods. And suppose if you see the silicon nanowires or carbon nanostructure, or sometimes templated approach, or if you see the fillet, graphene or graphene type materials, people can get the things. So it's very important how to prepare the materials. You can prepare the material by either by chemical methods or physical method, or sometimes suppose, for example, suppose the metallurgist, I think they need, suppose you want to prepare in super alloys, or sometimes you need a spark plasma sintering, means high temperature sintering is needed. So, or super alloys, you want to prepare composites. I think there we need in addition to the like mixing with ball milling or any nano size initial mixing, at the end they need a nice sintered palette. So that is very important for the depending on the applications. Since like battery, some technique may be useful. So I'm going to summarize not all the method due to time limitation. I'm not able to discuss all the details of this method. Still, I'm going to focus on some of the important methods that will be very useful for you people to the explore. You can use this material approach for the different applications. Regarding thin films are concerned, for example, you can do RF sputtering or pulse laser, autonomic, or still we have some like chemical vapor deposition techniques, etc. we can use. And it is very important. In fact, I think so. Suppose if anybody want to in new research, always you to remember you have to check with the ionic radius and charges to balance. Suppose sometimes you want to dope some particular elements to element, make sure that charge and ionic radius is going to match. So then only you are able to get some new material. So suppose here itself we don't match. Suppose your size is matching, size is not really matching. So whatever the way you try, and we are not able to get a desired phase. Sometimes people they claim that they're able to dope. Only thing is the less than something like 0.0001 means at the end reality is that mixing is difficult and sometimes it's very difficult to get the real information. So real doping is means maybe around 5 to 10%. It clearly indicate that the materials can be processed. Remember, each techniques have been limitations are there. So that's why you have to see any materials engineer or metallurgist. You have to think depending on the available facility and depending on oxidation state and depending on what type of the applications. Accordingly, you have to use the particular methods. So regarding characterization techniques are concerned, I think we can use X-ray is a very fingerprint technique. We can use especially for any materials. You want to see the lattice parameter, or you want to see any impurities, or especially for energy materials, you have to make sure that we're able to get a cation mixing. For example, lithium is going to other metal ion sites. That way we can check the things. Or sometimes if it's a light elements, we want to see the atom positions, we have to do neutron diffractions. I think based on my experience, the X-ray it makes you solve your purpose. So that is enough. Based on the XRD, you can see the either nano size or not. By using the refinement, everything you can do the things. And sometimes you can do X-ray absorption, all the fancy technique. Regarding thin films are concerned, I think again it's a little bit complex. Thin films are compared to the bulk because the thickness is a few nanometers. Sometimes we cannot use this well-known technique or we cannot do the ICP. So mainly what people use is Rutherford backscattering spectroscopy. In fact, this is one of the well-known technique to know the composition and thickness. I'm going to explain some of the example in the future slides. And nuclear reaction analysis for lithium content and Auger electron spectroscopy to see the homogeneity as well as some elemental distribution, etc. we can do. And if it is a bulk material, people can do the either titration because sometimes see how the metal ions are there and induce a coupled ICP technique means plasma to see the analysis. And sometimes X-ray photoelectron spectroscopy to see the valence distribution of the atoms or depth. We can see what are the oxidation state, etc. So it's very important. This is a way to suppose if you're a metallurgist. So again, for them, or if you want alloys, I think there we need a nearly DSC means differential scaling calorimetry. Like that way, see depending on if they want to see the phase transformation, they need a high sophisticated DSC scaling calorimetry, or depending on the applications, people have to use the things. Okay, and it is very important density of this material because we need we have to see the particular material how dense. So we need although the very old technique people will not use. I think if the metal, it is very important to see the density of any material. For example, bulk material to see the density, and we can these are the IR, Raman, and suppose we have magnetic material, we need a skewed magnetometer, etc. Although it's a nanomaterial, we would check the surface area. In fact, this is where it will give information how the materials are porous, or sometimes depending on the how synthesis technique or depending on oxide, we can see the difference in the surface area. And again, at the end, we need a galvanostat potentiostat and one impedance analyzer. So in fact, remember this technique is very useful if you want to either solar cells or any sensor or any other application. I think this one technique we can, or sometimes fuel cells. the same instrument you can use it for the different type of the application, or you want to use biosensor, etc., etc. And the end we need a morphology studies by using SCM, and SCM is a fingerprint, or still if you have any, so at the end you want to see very high performance material, more depth we can do TEM, etc. And sometimes, especially work with thin films, I think you may need the what they call atomic force microscopy to see the surface roughness, etc. So I think one slide I'm going to tell about, since among all, since we are metallurgists or any materials, I can mention that X-ray is a very fingerprint, and SCM. I think these two techniques, it will solve your purpose if you want to do any nanomaterials or any type of the new novel material that made you life is very simple. So usually XRD instrument looks like the commercial instrument. In fact, this type of instrument already you have in your department, I think, so in metallurgy. So either sometimes we can do, sometimes we want to be in situ, we can need a beryllium window, or you want to see the pellets, something you can, so you want to see the phase transformation, you can do in situ sintering, either temperature heating and cooling, etc. So you want to see the how the material is going to, for example, how the phase transformation, for example, TiO2, depending on temperature, if it is unattached, duratile, or different type of phase transformation, depending on the material, you can check by using this in situ temperature setup. Or still you can do XC2 also. So this is a way, I think if people want to be more careful studies, people will do different type of these studies, and we need SCM. So these are the techniques, are the common facilities are needed. In fact, since people are coming from different places, I think X-ray is a technique I'm going to use more frequently. I would like to tell that how the X-ray looks like. For example, the tube, and these were sample holder. We can put the sample here with the detector. We can get the patterns. So it is very important you to remember the Bragg's law. 2D sin theta is equal to n lambda, in the sense that when X-rays are incident on the very sample, diffraction will occurs. Depending on what they call as the interplanar spacing or d values, we can get the information about the, for example, intensity versus 2 theta with different type of HKL planes. We can see that your materials are amorphous. Usually amorphous, we don't see any what they call as characteristic HKL lines, or polycrystalline or crystalline materials we can see. So what information based on the peak position, we can see the how the unit cell or peak intensity will give the information about the atom positions, etc. And for example, depending on the width, we can see that your materials are nano or not. If it is really nano, we can see more broadened. It clearly indicates that your materials are really nano. So that way, this is one way. This technique is very useful for you to do before doing TEM expensive technique. I think with a simple XRD, you know that this material can be used for the, for example, nano size or not. You can check. So another way, suppose for example, European polymer composite and nano, usually most of the cases we can see the amorphous, sometimes we may get broad lines. So that's why you have to see that that is due to the amorphous nature of the material. Again, sometimes we can complement, sometimes we want to see the amorphous material. So this is the TM data, and if it is a really small nanocrystalline, we can see this type of the circular rings, or sometimes improved crystallinity, we can see dot patterns. So usually the TEM is nothing but this circular ring divided by D divided by 2 and 1 over D. It will give the information about the D value. So what you are getting from the D, the nearest one belongs to this one. That way you can match. So that's why it is very important to know the XRD. From that you can interpret with TEM data, etc. And for example, we have nowadays a lot of the commercial software you can do either by refinement, if you have the how much what they call as the impurity of the phases, etc., etc. And so in my talk, I'm going to talk about sometimes the different type of the oxides. So for example, among them, most of the material, including all metallurgists or material science and engineers, we have only 7 type of the crystal system. Among them, cubic, tetragonal, orthorhombic, monoclinic, and hexagonal and trigonal, etc. So here I'm going to tell about briefly. Suppose for example, so these are periodic table. So sometimes depending on depending on the applications, or people can play with the materials or elements. For example, since you energy material here, the lithium and sodium is very important. Or sometimes 3D transition element, for example, cobalt, nickel, and manganese. These are the elements of our interest. still we can do, for example, titanium, vanadium, etc. Or sometimes if you want to use for the different applications, people can do. In fact, these are all the different talks are going to be given by the next speaker. So now I'm going to talk about one example in case of the oxides. Oxides, one method is called as the molten salt method. So usually when compared to the solid state method, solid state is like high temperature simple mixing of the oxides. We can get a respective. So the disadvantage sometimes due to what they call as the unreactivity, we don't get sometimes desired phases, or sometimes we get impurity, or we need a multiple heating and ground heating. So molten salt method is one of the approach. You can prepare the materials either by materials in crystalline pure forms or mixed layered oxide, etc. Sometimes catalytic material, etc. Usually, this molten medium reactions are controlled by chemical equilibrium much faster when compared to the diffusion controlled reactions. So usual practice is a simple step is that you take a nearly 6 to 10 moles of the molten salt, for example, lithium. I'm going to tell what type of the molten salts you can use. And you take a respective metal salt. For example, you want to use the titanium dioxide you want to prepare, you can use titanium oxysulfate or tin chloride, etc. you can do. And it's very important you put in alumina crucible and heat at various temperature, wash with water and filter and dry. So in fact, this is a way usual step will occur. So beauty of this technique is that depending on the materials, temperature also can play, and time, etc. I can do. And you don't need any what they call a surfactant. You don't need any expensive things. Still, you can with a simple what they call alumina crucible and with a beaker and with a simple thing you can prepare the material. In this way, I think if people want to do MTech or any students you can do. I think this method is a little bit simple, and then you can do the project, and at least you can get 5 to 10 grams of the sample. That is enough for you. Or still, if we can, in fact, 50 to 100 gram sample also we can prepare. So by using this approach in the lab. So these are the same thing. What I say, I took the sample, put it in a wax furnace, and again, if the iron contains stir it, wash water, filter things, and put the dry the powder, and again you can use it for the other applications. In summary, based on the salt and time and initial reactions, we can see the different types of the shapes and then different types of the what they call as the particles, etc. I can do. So these are the various summary we've been looking into this one. So either you can prepare energetic lithium containing compounds, or you can prepare sometimes photocatalytic, or these are materials you can use for energy storage, etc. And either you can prepare, for example, magnetic material. For example, how this sometimes people are using for the different applications, sometimes composites, or sometimes people can use it for the supercapacitor, etc. I can use. And the end, for example, some material people can use it for sensor application also, example, titanium dioxide, tin, all this one. And at the end, some of the ceramic materials also you can prepare. Due to time limitations, I'm going to tell about, I will start some few simple compounds so that will be very useful for you. Later, I can tell you what are the new compounds we've been prepared with different approaches. As we know that titanium dioxide is the more popular. I think people can use it for different applications because titanium 4+ to 3+. Here, depending on that, we can do some electrochromic solar cells and batteries and photocatalyst and paints and biomedical applications. In fact, these are some of the people next speaker are going to cover about the different applications. So here, this again, we try to prepare the sample by using I told that titanium sulfate. So here we can see, so nano size material nearly 280 degree, we can nearly 200 meters square high surface area. We can remember these contain no surfactant. Again, simple molten salt approach you can prepare. Any student can do. One day, one evening, you can come and put the sample in the furnace and go. Next day morning, you can come and filter the sample, and it will be ready for you. So you don't need to worry about the expensive what they call as a technique. For example, inorganic titanium isopropyl, there are hygroscopic sample. Here, this method is very useful for you people. Again, you want to do basic studies. You want to see how the particle size, for example, increase the particle size. We can see the what they call as the average crystallite size is going to increasing, and as a consequence, surface areas it will decreases because of high temperature. Automatically, surface areas to reduce, and we can do further studies. This is a way as a crystallographer X-ray it will give information about, for example, anodized to rutile means high temperature always will go to what they call as polymorphs, So you can see that A and C value is higher, that's why it's expanded. And rutile phase like that. Remember high temperature, so we can see the FWHM is more sharper when compared to the low temperature prepared sample. Again, we can see the TM, which will give the information about the increase in the trend in the particle. Anyway, we got the information, get it from the XRD. It's almost like close to the plus or minus what they call about 1 or 2 nanometer difference we can see in the error. So at the end, once you get the material, I mentioned that depending on the applications, pick the material. So now your material is ready. So usual practice is that you can take 78% of your material and 15% of the conducting carbon, and PVDF is a binder to make a what they call nice contact. And finally, by using the ductor blade, or you can take a small glass slide, you can coat the sample either if it is the anode material is a copper foil or aluminum foil, you can coat the sample. And finally, then dry in the oven and we can twin it. It's very important. You have to make a nice contact. That's why we have to use a roller. And finally, punch into 16 mm dia. And finally, these electrodes, you can use it for the, we put it in the oven and dry the thing, and you can use it for the coin cell fabrication. So remember, usually either large scale, including our warehouse people, large scale batteries or any industry, always they will try to do with a small scale. As academic researcher, always I'm suggesting you try to do with a small coin cell type of batteries. I think that will be enough for you to how this material is performing well or not. Since the promising, if the material is really good, I think you can do. I think many people are interested to collaborate, or industry also interested because they have some limitation, for example, performance criteria. Once it's matched, many people are willing to what they can collaborate with you or take your technology. I think people can adapt. So important way how to fabricate cell is that, for example, we take this either coated electrode and put the separator and then the vertical lithium metal or the graphite anode. And finally, we can put the top cap and finally we get the cell. So this cell is ready to see how the performance, for example, as a battery, we want to look for the performance. For example, usually what they call as we can study. Before going to study the performance, since people are a little bit new people, I would like to tell the principle of how the lithium battery works. As I mentioned, it contains usually practical batteries, lithium cobalt oxide, or graphite, or sometimes lithium metal if you use a polymer batteries. During charge, what will happen? Lithium move from one side to another side, whereas the electron will pass to the external circuit. During discharge, again reverse reaction occurs. That's why what they call as cobalt 3 becomes 4+, they call oxidation reduction. That's why we call as a rechargeable batteries. That's why, so exactly like the same thing. So during the discharge, once the lithium is going, we can see the voltage difference like that way. So this is one example for the nanomaterial we have been prepared, so that here we can see that if you go for nano size to submicron size, we can see the difference in the performance. So for example, nano size prepared 280 degree, reasonably good high surface, and when you heat the same sample, nearly 750 degree, like although we'll get capacity fading, and nearly around 880 milliamps. So this way you can tell that your material is either nano or submicron size, depending on the application. People can use these things. Again, for example, sometimes depending on it, although I know that everybody cannot do all the research area, one person cannot do. So that's why it is very important, since you people are either metallurgists within the different faculties, depending on expertise. I think some people are working in solar cells. I think it's nice for you. Some if your materials are very promising, high surface, it's nice to collaborate with the within the faculty. So since again remember, since you are academic researcher, sometimes I know it is very difficult to compete with silicon because already technology is demonstrated, and sometimes thin film solar is already the world technology demonstrated. In fact, this commercially we cannot do much thing since it's an academic researcher. So best way that I think nowadays people, I think either if you are organic chemist or dye-sensitized solar cell or perovskite solar cell, there are 3 areas people have been. In fact, now recently the perovskite solar cells people are working. In fact, one example I'm telling that since it is a depending on the, we know that titanium dioxide is a semiconducting material because the white colored compound. In fact, not only TiO2, SnO2, and Nb2O5, etc. So what we do is we just collaborated some with the mechanical engineering department in our material. So they checked that really how the we can see the small improvement in the what they call as the efficiency. So that way, so here depending on application, for example, TiO2, I think we need a porous sample, either nano size materials is needed for the what they call dyes to enter in a particular material, so that automatically
हेलो रेडी सर एक्सक्यूज मी रेडी सर आपका ये अनम्यूट करो सर प्लीज सर अनम्यूट योर लैपटॉप डॉक्टर रेडी
Yeah, I'm not able to hear the audio.
डॉक्टर रेडी
Not able to get the audio.
when it happened now, just now, sir.
Yes.
Hello. So now it is clear, sir. Now it is clear.
No, still not.
Yes, now audible. Yes.
I don't know how it is. Somebody has did. I didn't do anything. Maybe probably. Yeah. I didn't do that. Okay. Sorry. Okay. Shall I start? No, my slide can
Yes.
move. Sir, my slide can move.
Yes, sir, I know.
Hello, sir. My slide is visible.
Yes, sir. Slide is visible.
No, I don't see much. Okay, sure. Okay. I'm sorry for. I don't know how to. Okay. So now it is visible, sir. It's okay.
Yes, it is.
No,
visible.
yes, sir. Yes, you continue, sir, please.
Okay. Okay. Just if anything, please kindly interrupt me. Okay. Sorry for the. Okay. So I didn't do. Maybe probably. Okay. Okay. So again, the titanium dioxide, depending on temperature, you can say. So here one example, I can tell that you see that since people are working nanotechnology, that's how the X-ray is very useful. See, for example, 240 degree, we are able to see nearly 3.2 nanometer. Again, 450 degree, 8 nanometer, and 54 nanometer high temperature. Automatically, we can see the broadening of the line. Whatever I discuss with X-ray, I think sometimes is very useful. So you don't need to go to do TEM. Once you are happy about this, what they call as the performance. Still, if you at the end you want to publish the things and you can do the TM. So what I'm suggesting is that I think X-ray is very useful tool to, or if you see the materials are nano size or not. Again, we can do the TM. We can do the similar trend. Sometimes we can see the difference in the shapes if you go for the high resolution. So again, for example, if you want to, in fact, since the already new world one, I don't discuss. Already we did batteries. I don't want to discuss. So still, this SNO2 people want to, for example, SNO2, AO2, all people can use it for semiconducting sensors. I think, or depending on different type of oxide, people can use it as a chemical sensor, but depending on the applications. Again, sometimes people want to do, for example, SNO2 composites. People can use these materials for the CO2 sensing applications. So another example is MnO2. In fact, MnO2 also the people have been usually people use hydrothermal bomb. So best way that you can use the same molten salt approach. You can do the manganese sulfate, or sometimes you can use the polymer precursor. Just you see what is going to be happening. Again, remember raw type of the morphology we can get by using this approach. Again, and using the polymer, we can see the difference in the what they call as the morphology. Again, so what I'm telling that sometimes depending on the which composites you want to do accordingly, you can design the things. And another way, see again remember the temperature is 180 degree. So again, all the temperature becomes spherical. So I don't claim that this you have to be careful depending on the molten salt and temperature. Depending on that, we can see the difference in the morphology and etc. Another one is the spinel containing samples. So again, so you can try to prepare the sample by using the salt. And so what I'm going to suggest you here is that by varying the salt, for example, cobalt sulfate or cobalt hydroxide, or depending on the what they call as quenching speed, and we can see the difference in the, for example, some cases we can see the composite oxide in the sense that we can see two type of the phases also we can see. For example, here, for example, another case and quenching, sometimes we can see the small impurity of zinc oxide, etc. So in summary, this is useful to see the difference in the lattice parameters, and again density of the samples, and at the end we can see the BET surface area, etc. AEM is also very useful technique. Again, composition, etc. So these are the what they call as the performance of the cells, for example, depending on the sample you can do. So one example, I'm telling all those same salt, depending on temperature, we can see the cubic to hexagonal phase transformations. So this is a way.
Audio.
Once again, the same issue, sir. We are unable to hear the audio, sir.
Suchania, sir.
Yes, sir.
The audio is lost.
Now it is okay.
Yeah. Now it's okay.
Yes, sir.
So I think what happened is that probably remember my name, so don't unmute my account. So that is the one thing you have to do. Some people are doing probably. Try to
something like that.
Okay, sir. Continue, sir.
Okay, so I can continue. So now I'm going to. Sorry for the first time it happened. So now we'll go for the. So my voice, my slide is visible, sir. Yes.
Yes, sir. It is visible.
Okay.
Clearly visible.
So now we are going for
Yes,
although
sir,
compounds are a very simple one. Now we go for the complex compound. In fact, these are the new materials. So although you don't afraid about the by seeing the formula still. So as the materials are materials metallurgists, depending on the what they call the materials synthesis, we can prepare. We can design the complex oxide. Idea here is that although these are the metal cluster compound here, molybdenum is there, so we can see the various oxidation state. So also and interesting, for example, electrochemical. These are the new compounds. First time we've been explored in the literature. So here remember, so there we cannot use molten salt. Here we would use the carbothermal, means carbon. Remember here molybdenum is in 4 place. I told you. Usually, suppose you want to be commercially, people want to prepare some material. Usually they use a seal tube reactions. Try to prepare MOO2 means reduced to 4 place. And use some expensive technique, and you seal the sample and put the sample in high temperature and you to get a respective oxide. So what we do the same this approach, try to avoid more simpler way. So use a carbothermal reduction approach in the sense that you take MOO3, react with calculated amount of the carbon, and finally we can get a respective mix all the compound. We can get a respective metal cluster compound. So remember. So the beauty of this method is that you don't need any seal tube reactions. Still with a simple tube furnace with argon atmosphere, we can prepare the material. Remember any carbothermal reduction method or anything, make sure that in minimum temperature is 750. Don't try to prepare sample low temperature, it will not react. The carbon has to react, I think based on our experience, minimum 750 degree, or some cases we can go to 700 degree. So remember this logic behind this one. You can take any material, make sure that depending on oxidation state, you can try to prepare the complex oxides. So these are the X-ray. As I told that we can do refinement. We can see the, for example, some cases small impurity, for example, different phases also we can see. Remember, if you use working with anodes, small impurity, it won't make much difference, especially for cathode. We get a pure materials that is very important for the applications we are going. And anyway, we can do as a metallurgist or material engineer, as you told, the X-ray is very useful. We can see, for example, lattice parameter we can evaluate, and we can see that you can compare your JSPDS patterns, or sometimes some materials are not really matched, and you can calculate nearly close to the materials we can prepare the things. Again, remember, for example, holmium or manganese, sometimes these are the C is expanded. That's why we can see elongated CX, that's why 10. And depending on the, for example, the lithium, holmium, we can get almost like A and C values are lower. Again, you can do the TM. You can remember these are crystalline materials, and with the patterns we can index the things. And again, anyway, based on the XRD as well as the TM, we can see the material, what they call as a despacing, etc. We can do. And at the end, sometimes your physicist or physical properties, in the sense that we can do the IR and Raman, especially in terms of temperature, how the we call Raman bands is going to vary. We can study. So this techniques may be useful if it is more on what they call physical properties. Although this technique may not be really useful for what they call as energy applications, still it is very important to understand the physical properties. And sometimes we are able to do. But with the physicist, we can work with these materials, especially magnets containing compounds. You can see ferromagnetism on TC about 39-degree temperature. And this way, I think these are a little bit and more on the what they call physical properties. At the end, I think the same materials we've been look for the batteries. I'm not going to discuss too much details on this one. Again, for example, instead of carbon, you can use a what they call a graphene thermal reduction. Means you can use RGO, means expilated graphene. You can do. You can put the material. I told you the 650-degree, depending on the oxide. You can prepare a complex oxide. Advantage of this technique is that we can prepare a reduced oxides as well as a graphene coating we can get. So that is the beauty of this this method, and we can get a different type of oxides, starting from simple and complex compound, etc. And you may ask you that why don't you use with the graphene alone for the batteries or energy? So I can tell that as a battery specialist. So no, because graphene alone we cannot use, because we can get high ICL and what they call irreversible difference between charge and discharge, and we don't see this plateau like. That's why we need a good applications. We have to get a plateaus with a lower voltage. That's why sometimes, although people have called this all the graphene, still graphene people are using for the energy application as a what they call composites, or people can use it for the different type of applications, starting from energy storage or sensor, etc. Sometimes what they call as composite, means mix of graphene, some oxide. People can study the things. Again, I'm going for next another type of the novel oxides. So as we can see that vanadium containing novel oxide, in fact, these are the first time we've been reported in the literature. So you may ask you that lithium iron phosphate is already known because commercially available. So we look for some vanadium containing phosphate. Again, the beauty of this one is 3.5 to 4.5 electrochemically for 4.1 volts we can get. Automatically we will get higher energy density is good. Although sometimes we claim that mechanism material is really good. At the end we can see this, for example, this sample we prepared in a different approach. For example, in potassium containing, these are simple complex oxide. Don't be worry about this big formula. Here we can HPO4 oxalate. These are the organic, inorganic complex moieties. And remember, these compounds we can prepare by using either simple vertical. You can take a beaker with a tartaric acid source. We can reduce this thing automatically with a simple magnetic stirring you can do. And remember, we have to get rid of the water, because the batteries or anything energy storage, we have to remove the water. So we don't want water. So again, remember, minimum 150-degree heating is needed to get rid of the water, and we can get the new formula. So again, we can do either by SCM, XPS. There are other physical studies people can do and see what example, for example, presence of the metal ions or the oxidation state, etc. And interestingly, these are the, I told you that nearly 4 volts potential we can get, and around nearly 110 milliamps. As you can see, for example, at the end you may ask you that in engineers are, oh, why don't you use this material for applications? I can tell no. Why? The reason is that for the what they call benchmark material, although we claim it as a new material, the benchmark is around 150 milliamps or 130. So that's why still we are a little bit what they call less than the benchmark material. Although sometimes that's why sometimes, although we climb to very high, very fantastic material, in the reality, if you go for real industry, I think they look for the what they call high capacity, all the high performance is needed for the real applications. Again, we can do lithium containing other type of the fractals. That's the way you can do. And another containing vanadium phosphates. In fact, these are the new compounds we can prepare hydrothermal. So idea here is that we can see the phase transformation from the orthorhombic to tetragonal phase. So beauty of these compounds is that although interestingly we can get nearly 4 volts potentials, as well as these are the lattice parameters I discussed, and you can see the nearly 4 volt potential we can get, and reasonably good stability, nearly around 110. and almost is usually for any battery or cathode, what they're looking for the good reverse redox potential means positive current, negative current, clearly indicate that this material will be really useful. Although sometimes theoretically is 166 practical, although sometimes we can calculate theoretical capacity, we are not able to get the near theoretical capacity. Sometimes that's why there's a big problem. Any new materials we will do, sometimes we can calculate theoretical capacity. Practically we will not get that type of that much capacity. And again, these are also new formula, don't be afraid. So again, HPO4 means it is like a phosphate. So what I discussed with is this is a H3PO4 compounds to HPO4 to HPO3. So these are all the just different might, although it is like very simple. So again, the electrochemistry will be different and performance is different, and you can try to prepare the sample. So these are also triclinic. Triclinic already I mentioned that it contains A, B, C means all will get. So if it is a different lattice parameter, and these are the things we got it from the X-ray diffraction instrument, and we can do the refinement, all this one. So these are the new formulas. So just we check depending on the literature, and we recheck with respect to close structure shift file, and then we re-refined, and we are able to get a what they call a new formula of the materials. And these are the different type of crystal structure. So again, we can see that these are all like, I don't tell that is the nano size. So these are the submicron size, almost like a bigger size particle bulk pellet. So we have to crush this one by using either by crushing or by using the ball milling approach. And sometimes due to here the stability of this material, although sometimes there is a problem with the capacity fading, that one to be solved. In fact, since these are new compound, I think nowadays the literature based on this report, I think many people have been looked and worked on relooking this type of material. I think people are getting the good performance with respect to what we reported for the first time in the literature. In fact, now I'm going for the nitrites. I think nitrates are the very fascinating compounds. So in fact, you can see the nitrates we can prepare by using variety of applications, starting from microelectronics. For example, you need metal nitrate. These are all things. And for example, nitrates, for example, zirconium, titanium, osmium. These are the, for example, people want to use for the visible and longer wavelength, for example, plasmonic applications. I think people have been studied. Since there is extensive research are there, in fact, including gallium nitride, a lot of things. So now I'm going to, I'm not discussing about this one. So for energy applications, what are other nitrates used? In fact, oxides people have been looked at, for example, cobalt oxide already known. So in fact, for the first time in the literature, we look into this system. What don't you use for nitrates? Advantage is 3 lithium can be reacted. So we can get high energy density, high capacity. Before starting this one, we try to prepare the samples. We started with the thin films. So again, small one slide about how thin films you can get either by using chemical vapor deposition techniques or physical vapor deposition techniques, or sometimes we can get a fancy techniques by ALD. So in fact, so for the laboratory, since we have facility, I told you the facility is available, we used a physical vapor deposition techniques. In fact, the advantage is that so with a simple, with a vacuum and with large area crystals, we can put thin films, we can get the things. Again, one small slide, important information. Depending on applications, we have to optimize the thickness, composition, understanding the electronic and surface and interface mechanical properties are in this. So these are the general point if people are looking for the any thin films for the different type of the application. In fact, this slide may be useful. Those people are doing for different areas of the applications. So it is one slide. Suppose if you have sometimes with hygroscopic samples, make sure that you try to use with sputtering unit attached to the glow box. That way you can do, or sometimes some oxide samples is not really a problem. Again, you can play with the physicist, power, lot of things, and then this target on partial pressure you can vary either oxygen or nitrogen or anything you can do, and distance, etc. And finally we can get the composition, deposition rate, and we can see depending on applications we can study the either physical and mechanical properties. In fact, one slide I'm going to tell about. In fact, this is a little bit very important technique. It's called Rutherford backscattering spectroscopy. So this technique is like more physicist people will use. For example, you need a Van de Graaff generator. Here, I think India places like Bark or Bhopal, they have the Van de Graaff facility, or some places in Calcutta. So usually helium beam is hits on your thin films. So what is happening is the backscattered electron, it depends on the atomic number, means higher the atomic number comes scattered first. So best what they call with OSHA, Raman, what they call RAM software, we can calculate the composition thickness as well as the what type of composition, what are the elements are there. We can do simulation. This one you can do. So in fact, I can tell that the RBS is a very useful tool if you're working about the what they call a small nanometer type of the thin films we can do. I think this is very useful to know the composition and technique. Again, you can do profilometer. I think this is one more technique is very useful for the material scientist. You can do the things. So one example is the cobalt nitride materials. So as I mentioned that what is our motivation? So we are oxide people have been reported in the nature. So again, 2 lithium. So here nitrides, we can expect the 3 lithium. And sometimes we can see that high capacity. That is the way people can do either physicist. We can try to sample by the RF sputtering. And these are the various sputtering conditions, for example, 150 watts and nitrogen partial pressure. Remember, always sometimes a new research, still it is a nice, good idea. I think finally end up with, although sometimes creative ideas it will work. Sometimes I don't claim that already we tried to prepare, like luckily cobalt nitrates we are able to prepare. Again, we tried all those very simple compound. Why don't you try with the iron nitride? Somehow iron nitride we are not able to get a single phase. So we can get Fe2N and some other phases we can get in. Okay. So these are the XRD pattern. Again, it is simple cubic structure. And we check with RBS pattern. So we can see by using the cobalt and nitrogen. Again, the samples are coated in the thin films like silicon substrate, or suppose if we do with carbon substrate, we can get a beautiful splitted line we can see. Again, best way is with our RM software, we can calculate the thickness as well as composition of the sample. So again, if you want to see nanoflake or not, with SCM and TM things, it will clearly tell the information about the what they call as a despacing as well as the morphology of sample. Again, so reasonably almost like 1000 milliamps, reasonably good. Again, at the end, although these materials are very performing, we have to reduce the voltage for the real applications. This is my own conclusion comment I'm suggesting for the any young researcher want to continue this type of material is how to reduce the potential is a little bit question mark for this type of the oxides. And anyway, you can check with either by cyclic contamination to see the reversibility. So these are all techniques you can do once you go more detailed. Another one is, for example, bulk is a very good question because how to prepare thin films is very easier since you're preparing the sample in a small scale. So if you prepare in a bulk means, suppose for example, that is a little bit important for the material engineers. So best way that you prepare oxides. So remember the beauty of this like method is we can prepare large scale. So here materials should be very porous. Suppose sometimes your materials are not dense. For example, you take commercial CO3O4, pass the ammonia gas, it will not get prepared for that. So make sure that ammonia has to penetrate into the sample. Should materials try to prepare a porous somehow, whatever the way you try, material should be logic behind the porous sample. So the ammonia has to penetrate and we are able to get react with ammonia to form cobalt nitrate. Remember, don't use to high temperature. So I think 300 to 335 is the best temperature for cobalt nitrate. Suppose if you try to high temperature, you will get a cobalt, what they call CO2N is a metallic nitride, and cobalt mixed phases will get, so it's not really good for the applications. Maybe some other application may be okay, but really this for energy application, this may not be interesting. And suppose you want to do some doping concept, you try to prepare NiCO2 pass the ammonia gas, and we can get a respective what they call nickel dope compounds. You can tell. Again, remember chromium nitrate is very hard, and we try to prepare the sample with low temperature, not form minimum 600 degrees needed. And if you want to pass with, for example, you want to prepare to carbon, and we can get a respective oxide also in argon atmosphere. So that's why we can reduce CO3O4 to cobalt oxide is in 2 plus, etc., etc. And this simple XRD, for example, NiCO2 with oxide is converted into simple cubic nitride. Okay. Example, these are similarly cobalt nitride. And we check the lattice parameter as well as the X-ray absorption fine structure. So there we can tell that what it will do is that based on the reference, we can see the cobalt cage closely is matching with respect to the standard compounds or not. So as the energy storage applications is still we've been focused with the different type of things, and reality I think is very interesting material. Then at the end for the large scale applications, we have to reduce the potentials for the real applications. In summary, if you go for nanoflake to the bulk material, and sometimes we explored about titanium nitride when iron nitride, somehow these materials are not promising for the energy applications. Again, I'm going for alloys. I think alloys is a metallurgist. We are able to think about how to prepare the materials in alloys. So alloys are very promising. Suppose you want to So again, alloys in terms of energy. In fact, a word of alloy is a little bit metallurgists will think about different way, in the sense that you want to prepare a ceramic composites also, for example, aluminum, carbon type alloys, but different type of applications people can use. So here I am talking about alloys in the sense that we are able to have only silicon, tin, aluminum, indiums, alloy forming elements are there. So these are the voltage and expected theoretical capacity. You want to prepare any new material design, make sure that it contains this type of the elements. And sometimes you can make a composite, for example, silicon mixed with aluminum with what they call spark plasma, different techniques we can do. So beauty of this, although we can prepare, you remember, it's very important material should be nano size. Otherwise, if you have micron size or big, really it will not work. Whatever the way you prepare, so this is really difficult. So alloy should be any alloys, any metals or oxide should be nano size materials only. It is very important. So what will happen during the usually we can see volume expansion and contraction occurs. That's why it is very important. Material should be nano size. We can reduce the lesser volume variation, etc. So one of the new compounds we have been reported is, so again because VSBO4 is already reported. That's why sometimes we can get some idea with the literature. Again, why don't you look into the antimony? So we reduced to tin containing oxide because also tetragonal isostructural compound. You can try to prepare by using this approach. Again, we try to, again, since a new compound, always people will try with the solid state reaction. Once they're happy, then people can do with a different type. We can reduce by particle size by using ball milling approach. In fact, you can reduce here. This is a way a lot of metallurgists or mechanical engineering department people want to reduce the particles. For example, any alloy containing material want to mix it. I think people can use the mixing the sample by using the alloy, because, for example, or they call it agate, or depending on the material, people can use a different type of the balls or different type of container to avoid the contamination of the sample. So this is one example. You can tell if you see the micron size to nano size, we can see XRD, we can see difference in the what they call line broadening, we can see, and we can see the difference in the crystallites size, etc. And we can check with respect to the TM and almost like and surface area also, we can see the difference in the what they call as nano size material, slightly higher surface area, etc. So this is one example. If you go for micron size to nano size, see, micron size seems to be a little bit more capacity fading when compared to the nano size material. I think we propose different type, what is the real mechanism, and we check with impedance. It will give the information how the resistance of the cell with long-term cycling. I think that is the way it will give the information about the sample. And another way, I told you the alloy, we can use the same concept. You can use iron, indium containing materials, and we can try to prepare the samples by using this approach. And it is one example. If you go for the what they call submicron size and nano size, it seems to be the one example you can tell that if you go for nano size to submicron size, these are the way we can do. Since this is a way some nanotechnologies people can do. In fact, still I'm thinking that if people are interested, we can try to use, although since a new material people can do, for example, sensor application. Maybe I'm thinking about vanadium containing antimony samples are more promising for sensor application also. Okay. I think one more new compound, again I'm telling that these are new, first time we've been reported with a tin containing hollandites, although it's very complex oxides. So beauty of this one is that here tin containing alloy elements is there, and cobalt and indium. And again, so we try to prepare the samples. Again, as a first research is, if you new things, always start with the solid state method. You want to reduce, you can use the ball miller, try to reduce the particle size approach. So again, remember these are the complex oxides. We need high temperature sintering. We are able to get the sample. Again, we can reduce the particle size by using ball milling approach. We can get nano size materials. You can see because the bulk material is like bigger particle. Nano it seems to be broadened lines we can see, and these are the various way as a material researcher, or you can do the. That's why sometimes X-ray diffraction technique is very useful. And these are the various what they call tetragonal lattice parameter, etc. And these are the hollandite type tunnel type structures. So that is very important for the what they call as lithium diffusion, etc. We can do, and anyway we can check with the TM. So it is like complementary. You can see the your materials are nano size. And interestingly, for example, cobalt and indium containing samples are reasonably good performance when compared to the almost like nano size seems to be a little bit better performing material when compared to the bulk material, etc. Is a way, so sometimes what they call alloy means this is very important. you have to think about with good application with point lower and higher voltage reversible peaks, and voltage should be lower. So that is the way. If you want to be used for energy application, make sure that material should be low potential and should be reversible peaks for the real applications. Again, sometimes we want to see mechanism because you can see the lithium, lithium tin alloy formation also we can see. Again, remember these are all becomes amorphous when you are the nanostructure while doing the electrochemical cycling. And TEM we can see sometimes a little bit complicated, still people can do, especially TEM, cryos TEM, lot of things is happening. I think recording TEM with the cycle electrode is a little bit challenging according to my experience. Another, I think, type of nanostructure people can think about. So if you want to prepare in the fiber type, for example, nanostructures, we can grow it in a current collector. So best way is that we call vapor transport technique. You can use zinc oxide and then SnO2 by using the carbon as a source, and we can prepare the sample. We can get a respective nanostructure. Since the topic is nano, so I'm telling you about really nano. Still, sometimes without nano also you can get this performance. So overall summary is that these are the expected lattice parameters, and so I can see that depending on the what they call nano type of the morphology we can retain. Again, we may ask you that about cycled one again becomes nano becomes submicron size, etc. So these are the examples. So since alloys with higher voltage, although after few cycles the capacity disintegration we can see. That's why sometimes, although many people claim all nano will work, not really true. You have to be careful about which voltage you are cycling. Accordingly, we can use it for the different applications. The nanowires, or sometimes we can use the nanoplates. Sometimes you can prepare by using the chemical approach. Also, you can do. Again, we can get this slight difference in the performance or some improvement for. In summary, suppose you want to see what is happening about the what they call after cycling is very important. You can see what you are getting from the fiber type of structure becomes after 15 cycle or disintegration of material because smaller particles is happening. As a consequence, that's why sometimes capacity is fading is due to the smaller disintegrate and remove what they call as materials is going to be removed from the current collector. As a consequence, we can see the small capacity fading. That's why there is a big problem for the. So it is not really good. You want to be stable capacity is needed for the real applications. So since my time is a little bit finished going soon, so that's why I'm going to touch about some few quickly on the what type of metal fluoride and oxides. So usually olden times, I think we won't prepare metal fluoride. We need a HF and with metals. So it's very corrosive, and if you use a Teflon beaker. So anyway, they can use this type of, for example, initially we tried oxyfluorides also we can prepare by using this approach. So recently we've been looking into why don't you use some Teflon containing PVDF, because you know that polyvinylidene difluoride is a fluorine containing source. We can use excess fluorine, for example, 100% PVDF. We can prepare by using this type of the respective fluorides. So this is a way, for example, this fluorides people want to be photocatalysis. I think maybe more promising. For example, although batteries may not be explored in future application, I think people can think about. So what I'm doing that always any listening the topic, sometimes depending on the area, I think people can adopt this some particular concept. I think people can use it for the depending on the research, and then people can use it for the different applications. Again, I think as the things we've been looking into this type of energy storage, and also we see the in situ XRD and with impedance and how the with respect to voltage, how is going to vary like that. Since I don't have time, I don't want to discuss about the next slide. Again, TINF is what they call as recently, I think olden time. Remember, titanium nitride is a little bit difficult to prepare. So sometimes people are calling nitrogen fluorine based compounds. Sometimes we've been explored. So since the prepared material is green in color, so we try to prepare the sample, although we thought it is like TINF at the end by literature and then reviewers suggested. I think we look into the system. So it seems to be TINF is very difficult to prepare by using any literature is not existing. So that's why sometimes, although people can, so again, this type of promising type of material, people can use it for photocatalysis as well as energy storage. So that's why sometimes some materials may be used for the different applications. Again, we can try to prepare by using ball milling, or you can either anatase and what they call nitrogen fluorine doped samples. So anyway, these are the lattice, what they call particle size, etc. We can see, and then so this is the way what they call intercalation limit for this type of the match. So since I talked about too much on batteries, I'm going to skip this type of too much details on this system. So I'm going for the next system. So in summary, what we learned based on, I think this purines like containing materials also we are able to prepare. So again, so here one slide I'm suggesting that since we are a metallurgist or materials engineers, so for example, ceramic material, for example, people want to use for solid state because there is a spot plasma sintering we need. So we need all type of the oxides to press together. We have to get a energy device. That's why, because of safety problem, people are thinking about how to prepare a composite batteries without doing what they, with the metallurgist, how to design that one is a real challenge, you know. So we know that many ceramic materials you won't prepare in large scale. For example, this type of paper sheet type of material is very difficult, you know. For example, either use any technique with a ceramic because of mechanical stability, there's a little bit problems are there. So you have to make sure that material should be more mechanically stable, and we need a good conductivity. Means some particle to particle contact is needed. I think these are the various approaches people are doing. In fact, it's very important. Thermal expansion coefficient is to match with cathode and anode. These are the very important criteria, because since we are sintering with high temperature, for example, spark plasma sintering, or by using simple hot press, or by using the pellet pressing with a re-sintering in the furnace, we need a. So it's very important. The major issue is that what the interface is going to be reacting with the material. So that's why it is a little bit challenging with the metallurgists or materials how to stop this what they call interface, which means well protected interface with it won't react the material. So there's a little bit challenging. In fact, these are a lot of the oxide containing garnets. In fact, these are all the sample with high temperature, nearly 800 900 degree or 1000 degrees. You need to make a good sintered pellet to improve the conductivity. Again, the same garnet people can use it for sensor applications or some different type of the applications. People again, I think this is one possibility for metallurgists to think. Since I'm going to think about another, I think another 5 minutes I can take. Since other applications, since I don't have time to discuss, since some of the work, in fact, third speaker is talking about this area. I'm not discussing too much detail. Again, there is a positive, since people want to replace by sodium, by lithium. The same concept, once your expertise and people can do. Again, each technology, for example, sodium is cost-wise is very low. And again, the voltage is a little bit, we get lower voltage, that we have to sacrifice, no other option. And for example, one example, you take the lithium compound respective, you get 4.2 volts, we can get nearly 3.8. It means that we can reduce the lower voltage. That is a little bit we cannot avoid, so that is a little bit big problem. And these are the some new work recently we have been looking at the system. Anyway, I'm not discussing, this is not a really new material, so I know I'm going to skip this one with this type of the slides. I think one more last slide. I think sometimes people don't have much expertise. People can do supercapacitors. Again, you take some materials or some nanostructure materials, you can play either carbon or metal oxide. People can, in fact, there's a lot of wide literature is there still. Is a positive. This is the way you can tell you that some people have university. People don't have much facility. The simple electrochemical setup with aqueous electrolyte also you can do the research, and also with a simple beaker you can do use of applications for nanomaterial. Again, you can play with different types of oxides, and these are the anyway. A lot of wide literature is there. I don't want to still here the nanotechnology will play an important. People want to see good contact and the tech structure is needed. And you can play with the electrolyte, etc. And sometimes for this application, you would coat the sample in the. Already I mentioned the nickel mesh is needed to coat the nanostructure material and see the performance. Again, sometimes, for example, people are working for the electrocatalysis. Sometimes very important. Sometimes I know that sometimes all people cannot do. Still, is a nice opportunity for the sometimes electrochemist or whatever the metallurgist. Since your facilities, you can think about. In fact, this is very important for people are working for this type of electrocatalysis, or you want to use for lithium air cells or something. Catalyst will play an important role for the applications. I think I'm going to skip sometimes sol gel. So these are the, in fact, these are the old people. Suppose you want to be the combustion synthesis or co-precipitation method. Suppose you want to prepare a large scale simple burette and beaker. You want to be complex oxides. You can mix this in. This is a way what they call as a recipe to make a mix with the materials in the two, if you have 2 to 3 elements are there. So best way you want to make solid solution, 3 elements are there. The best way is that you prepare the sample, precipitate this thing, and you can heat the sample. This is a way to get a simple homogeneous materials you can do. Again, the combustion method, you can play with either fuel, oxidizer, and sometimes you can play with the surfactant, etc., etc. You can do, or you can do sol gel method, etc. Since my time is almost another for 2 minutes I have. So sometimes we can do, sometimes we can use a polymer. We can get respect to what they call raw type of the structures we can do. So, and some of the complex oxides you can prepare. In fact, these formulas are a little bit. And sometimes sometimes people are working nanotechnology, sometimes electrospinning. So this technique, I think people may useful for if working in the bioengineering or tissue culture. I think people they can use polymer type of nano spinning, electrospun for wound healing. I think although materials we cannot use too much, still the another type of this same equipment people can use it for the bioengineering applications or bio medical related research. And sometimes people want to use with fiber and then particles you can do. So I think this is a way people can get the material. Or sometimes you want to use the nano composite catalysis, etc. I can do. In fact, these are all the color composite material. Again, people they really need a size specific high surface area materials are needed. So these are the porous material people can do. Since so, and sometimes another way is the microwave. In fact, these are all, for example, as a engineers, this is a way to dissolve the materials in a homogeneous way, or sometimes what they call a fast reactivity we can get by using this type of the different type of the synthesis. Advantage is that microwave is a faster reactivity because the solution is vertical dissolution is easier, and then anyway these are the various type of mechanisms. So since my time is going up, so that I have to finish soon by another 1 minute. So this final conclusion is that efforts have been made. So look for the, especially in terms of nano submicron size materials for energy storage. The extensive synthesis literature is being done, and especially still is very important. Look for the novel material. For example, sometimes as academic research, any institute, I think it is nice for us to academic research look for new material. It's not so easy. By trial and error, we will get the things. So that is my suggestion. And again, in Word, I can enter for nanomaterials. Still, I can tell nanomaterial deliver the better performance than compared to submicron size. Why? Because what they call diffusion of the ions is easier. Automatically, we'll get the improved rate capability, etc. Still, again, we need a long, safe performance with novel materials are likely to come out. Again, it's very important at the end. Is a nice
Sir, your
Ready,
voice
sir?
is not
Please
audible to
unmute.
us, sir.
Ready, sir? Please unmute your system.
yeah. Now is okay.
Yes, yes, now.
Okay, I don't know what is happening. Okay, okay. I think now it is okay, sir. Okay.
Yes,
So,
yes.
yeah, in fine conclusion, anyway, I think these are the things we have been reporting in literature. Some materials are new. Okay, so I think now instead of, I think maybe I'd like to take a question and answer. I think happy to. Okay, I think another 10 minutes we can raise any questions. I'm happy to take the things. Okay, still feel free. So don't be shy. And then if you have really a problem, I think you can send me by email also. So it's very important. I think that is the way we learn. That is my personal experience. Is that. So always the conference or workshop is a nice medium to learn new things. And thank you for the organizer. I think this is very hard work. I think it's very important. I think with the different topics they are merged in a different. I think this is a really good one compared to my own personal experience with compared to the conference and this one. Conference only some 10 to 20 minutes is very difficult to learn because the slides will go very fast. I think the workshop is the best way to, especially for the new researchers or young research. Already people are doing the research is a good way to pick some new points. So that is my personal opinion. Okay, thank you very much, and then I'm happy to answer some questions.
Thank you, sir. Very thank you. Any participant they want to ask their query, then sir is ready for that. Anybody?
Or I can check any share. Or if anything, then okay. So send me his
Sai
email.
Kumar Aturi.
Yeah, please. I cannot. So they can do chart also. I think that you can ask them to. They can do any chart also, so that I can respond also.
Yes.
Sir, no, if you don't mind, sir, I'm asking you for
Yeah,
your
please. Yeah, please.
mail it.
Please.
Mail
Yeah.
it and I'll discuss about later, sir, actually.
No problem. No problem. Okay. If any questions, happy to. Okay.
Yeah, yes.
I don't. There is an option for chart anyways. Okay. So that at least I would have removed.
Anybody? Thank you, sir. I think nobody want to ask this one. They are very listening your lecture. And one thing I want to ask, sir, suppose we want to add some high entropy alloy like that material inside of the polymer.
Okay.
Then there is possible to arise electrical property inside of the polymer.
Yeah, it is very good question, Martin. Thank you very much. I think that is very good, good idea. Not many people have been looking into that one. So usually this alloys and the polymer should be, I don't know, they should be conducting. You know, make sure that don't use whatever example PMMA. Try to avoid. And again, the polymer should be conducting. For example, PVDF or any conducting type polymer you can use. So based on my experience, in fact, I didn't discuss too much about the alloys. Some alloys we've been, for example, silicon, aluminum alloys we've been prepared. Somehow it should be nano size. You know, these little bit tricky about these alloys. You know, so should be nano size. Still, since some alloys, I already told you that alloys containing some cobalt and the matrix element somehow very well. So my suggestion is that yes, depending on the, make sure that the table should be careful about alloy forming element. Suppose you try with some other than alloys, so it will not form. You know, so it is a little bit. Although for the applications, especially in terms of energy, yes, you're right. For example, aluminum carbon compound. Still, aluminum we can get some what they call the energy storage due to aluminum. Small aluminum we can do. Especially other one is if it is dead mass, automatically we'll get it lesser theoretical. You know, so that one you have to what they call matching up this capacity. Little bit tricky we needed, and that's why sometimes what they will do is that this alloys metallurgist people have been attempted, and we also look into some for example the silicon based alloys with what they call as melt quenching, try to prepare and ball milling we can do somehow. The material should be nano size, you know, that's why it's a little bit tricky about this alloys, you know. Still, for example, silicon, if you take any silicon substrate, if you do battery, running the battery is really wonderful. Somehow it will not work, you know. This again should be nano size is needed. There's a big problem with this. Yeah, and again the what they call a cracking of the what the substrate will come automatically. Some few cycles, then the silicon the layer will come out, you know. So automatically the battery is going to be die, you know. So there's a little bit difficulties are there in this type of the alloys. And still I'm telling that as a metallurgist, I'm talking about there is a what they call as a, suppose if you have good technology to make any ceramic powder in a sheet type of forms, I think if you have a little bit technology at the metallurgy, I think that one you can made a patent, you know, that is a really nobody cannot do till now based on my experience. If anybody good ideas to make a sheet type of the ceramic things, that is really challenging, you know. Yeah, anyway, so as you know that we, I think anyway extends a lot of experience. Not many people look into this one. Sometimes we need a lot of metallurgy background with a particular ceramic processing with a large scale, you know. So that is a little bit. Again, we don't want to sacrifice, for example, reactivity. It's not like, for example, if it is a carbon-based alloy, for example, silicon carbon matrix alloys, so they are no problem. They don't care about because they are very reducing advanced. I think here lithium is there, it will react, you know. So these little bit difficulties are there. Yeah, including the spark plasma sintering, we have been looking into this one somehow. Yeah, so maybe some different people have, we didn't explore too much, yeah, because of manpower and that.
Yes, sir. Because polymer is now the need of today.
Yeah,
because
yeah.
resources
That's why,
are limited.
yeah, polymer
So
composites
there
still.
is some metallic property in the polymer.
Yes.
It can be used in place of some conductor, and it may be arises also magnetic property in that.
Yeah.
And they can use some transducers for the space.
Yes. That's why I'm telling that you to use this polymer, but forget about this battery. So that's why sometimes the metallurgists, people always, that is the way nanotechnology. Sometimes you can use this one, or for example, EMI shielding, or depending on the, you can contribute as that is the way metallurgist, depending on expertise, we can contribute in different ways. So that's why that is the way at least students are getting exposure. and they are learning, and that is the way we are contributing, sir. That's the only thing. Okay.
Thank you, sir. Very well. Thank you. And we will touch after this session also, because our students are doing the same work as you shown in your talk. So we will be also in touch during our session. Thank you, sir. Very well. Thank
Okay.
you.
Thank you very much, sir. Thank you very much, sir. Okay.
Participants, our next session is start at 2:30 p.m. and our speaker will be Professor Suresh Prakash Harsa. He is from the IT Roorkee. So please join the link we saw on this Google team, particular 2:30 p.m. There are different link for that. So link, join that link. And you know very well that AICT norms over the attendance during this whole session and during the 14th session. There is 80% is necessary for the attendance, and after then there is the assessment at the end of this FDP that covers 60%. You want to obtain 60% marks in that. Okay, so remain you are stick to the attendance as well as your assessment. If you failing to get this, you do not get the certificate from the AICT. So please maintain the attendance as well as assessment. Assessment taken the once in this whole FDP at the last. Thank you. We will join at 2:30. Okay. Thank you very much.
Okay.
Okay.
Thank you, sir. Ready, sir. Thank you very much. Thank you, sir.
Okay. Thank you very much. Namaskar, sir. Thank you very much. Okay. Thank you. Thank you. Okay. Have a nice day. Thank you.
Pressing out.